this proof, we're going to prove the distributive law of scalar multiplication over matrix addition. So it's a fairly general sort of proof, a proper proof. But before we go into that, I'd just like to go over a few things. This is important, and it also might answer some of the questions a few people had in the previous lesson. It's about elements of a matrix. So the elements of a matrix are each number or thing in the matrix. And they're referred to using a special lowercase letter. And it's usually a lowercase letter of the matrix's name. So for example, if we had the matrix C, we would refer to the elements in terms of small c. So general matrix C might be something like this. So we've got a uppercase C there, and we might have, it's often in brackets, so lowercase c and subscript I, j. And it can also be referred to in this way here. Again, lowercase c, I, j, for an m by n matrix, which is the dimensions of the matrices. So what we have is that this means that the matrix C has elements C, I, j, and is of size or dimension m by n. Okay, so that's its size, and it's also called its dimension or dimensions. So how come we have an I and a j and an m and an n? Why do we need all that? Well, think of I and j as variables. They change. So as with a matrix, okay, you would have elements. These are all lowercase, okay. Should there be commas between these little numbers? Well, we don't write them, but yes, it would be good to have commas there, but just because it's so fiddly and small with the subscripts, we don't write them. But that's not C11. Okay, that's C11. It's a bit blurred now. And that's C12. So yeah, you could think of it as having commas. It's to the point where we get the matrix filled. We've got, in this matrix, we've got, if it's an m by n, we've got n columns. Alright? And as we go along there, the little j, you see back to your left there, changes. So it's like a variable. Okay, it's not fixed, whereas n columns is fixed for a particular matrix. Got it? So the highest value of j could be n, but j doesn't equal n necessarily. Okay, only at the end does it equal n. Now, if it's an m by n matrix, we've got m rows. Okay, m rows, and along here I changes. In the same way, it's like a variable. It doesn't equal m, except for right at the end. It can go up to m. So I hope that helps a little bit. So it means that this matrix C has elements C, I, j in general, and is of size m times n. Proves the distributive law of scalar multiplication over matrix addition. It uses some of the nomenclature that I've just been talking about there. Alright, so what you need to do is write the worded proof into useful symbols in maths. So required to prove, the clarification basically. Now, what we have is R outside of A plus B. So R, this R here is a scalar. Okay, remember a scalar is a real number. And A plus B are matrices, hence the tildes. We have to prove that the distributive law holds. Now remember, the distributive law distributes what's outside the brackets amongst what's inside the brackets, to use a basic everyday description. So this is how it would manifest itself. But we have to prove it for all, remember that symbol, upside down capital A, for all R, which are elements of real number system. And for matrices A and B, which are of the same size. Because matrix addition is only defined for matrices of the same size. Okay, so that's a correct way to set up the proof. So the proofs can start now. Proof. So define your terms. So let matrix A so develop the left hand side. Close the square brackets too. Okay, so we look at the definition of matrix addition. Definition of matrix addition means we add corresponding elements of the matrices together, which gets rid of those inner brackets. Now, this is when we use, basically, because we've now added the matrices here, this is essentially two matrices added together, that expression there. We can now apply the distributive law for real numbers. Okay, so applying it for real numbers, A, RAIJ plus RBIJ. Okay, so it's applying the property for real numbers. Now, since we're looking at real numbers, we look at the definition of matrix addition. So it's kind of like we have two new matrices now. Once we put the curvy brackets back on, it's like we're looking at two new matrices again. And then we look at the definition of scalar multiplication, we're taking it back. Okay, so we can, it's kind of like factorising really, just looking at scalar multiplication, almost like taking a factor of R outside. Okay, and that equals sorry, this bracket's up there, plus that, you might have noticed, equals the right hand side. Okay, that equals the right hand side, you can see above. Okay, so what we've been required